Is Martin Barlow from BBC. Everything needs no introduction. He's going to speak on the scaling limit of two-dimensional UST.
Okay, thank you for the introduction. Sorry I missed the first day of the workshop. If people were looking for me, I had meetings in London. Anyway, so I'm going to talk about the scaling limit of the two-dimensional uniform spanning tree, and there's going to be a certain amount of introduction about the uniform spanning tree, which has been an extremely influential model in probability in the last 15 years, as you'll see from this talk. So let's just start with the definition of spanning trees. We have a finite graph, and there are three constructions of the UST I'm going to say something about. A direct construction from the FK random cluster model and from loop-erased random walk. And first of all, direct. Well, a definition of a spanning tree is it's a subtree which spans the graph so that every gives you a connected subgraph which is a tree and which contains every vertex. So you make a list of all the spanning trees. You make a list of the spanning trees. You choose one at random. That's a uniform spanning tree. So that's the direct construction. Then there's also a connection with the FK random cluster model, and I'm not going to use this in the talk, but it's useful to see that the uniform spanning tree is an extreme point of this model. So we take two parameters, probability p between 0 and 1, and a number q bigger than 0, and we defined a collection of probability measures on edge subsets as follows. So we take an edge subset, we look at the number of edges, that's NE prime, and KE prime is the number of connected components we get in the graph. And then we define a probability measure in this way. This is the usual sort of normalizing constant. This is a binomial type expression here, and then we weight it with this q to the k factor. If q is 1, then this term disappears, and a little thought tells you you've got IID bond percolation. Now let's look at the limit of 1, as we let p and q tend to 0. This term is not important. So basically, we want n and k to be as small as possible. So it turns out that since q is small, this probability here will concentrate on configurations which have only one component, on subgraphs which span V. And since p is also small, it concentrates on configurations with as few edges as possible. So it ends up that one gets spanning trees. And a little thought tells you that n plus k is bigger than or equal to the number of vertices. So a short calculation tells you that if in fact q is less than or equal to p, and you then let the limit go to 0, you end up with spanning trees. So the uniform spanning tree is a limit of this FK random cluster model, which also contains percolation, Ising model, and so on. So when we see the sort of connections in statistical physics which arise for those models, it shouldn't be a surprise that we also see them for the uniform spanning tree. But when we've let these parameters go to 0, there are no parameters left in the uniform spanning tree. So there's not quite the same possibility of talking about phase transition and so forth as there is in other models in this class. Now, the third way of constructing uniform spanning tree is from the loop-erased random walk. So here is a picture of a loop-erased random walk, rather large scale on the subset of Z2. You take a subset A of the vertexes, and you take a vertex X. You run a simple random walk in the graph starting at X, and each time the random walk forms a loop, you erase that loop and you carry on. At the end, you'll have got a path going from X to the subset A, and because you've erased all the loop, what you've got is a self-avoiding path. So we're going to call that LEWXA. It gives you a random self-avoiding path from X to A. So using loop-erased random walks, there was an earlier discovery by Aldous, Broder, and others that paths in the uniform spanning tree have the same law as loop arrays random walks, and following a certain amount of work in that area, Wilson gave the following rather nice algorithm to construct the uniform spanning tree on a graph using loop arrays random walks. So you take an ordering of the vertex set. You start off with a tree which just consists of Z0, and at stage k, you run a loop arrays random walk from zk to tk minus 1, independently of everything else, of course. And then you just take tk to be the previous tree combined with the loop arrays random walk. So to speak, you start off with a vertex here. You get some sort of loop arrays random walk going to the vertex. You take another point, you run it like that, and so forth. You might choose a vertex which is actually on the existing tree, in which case, of course, you don't do anything. So that gives you, obviously, it gives you a random tree, and a random spanning tree, and with some work, one can find that it also, in fact, gives you the uniform spanning tree. So in a paper on loop arrays random walk in 3 dimensions, Gardi-Cosma made the comment that of all the non-Gaussian models in statistical mechanics, LEW is probably the most tractable. And what I'd say is that because of the very close connection between UST and loop arrays random walk, uniform spanning tree is the next easiest one. So, of course, what I've done so far is just tell you about finite graphs. We want to take limits. So this was done by Robin P. Mantle in 1991. We do the obvious thing, which is we look at the uniform spanning tree in a finite box, and we let n tend to infinity. And there are some monotonicity properties which enable you to get, without too much trouble, a limit, a limiting law. And for general graphs, it may turn out that the boundary conditions you put on the boundary of the box could have an effect on the limit, but for reasons to do with the Liouville property of ZD, it turns out that for ZD, whatever boundary conditions you put on the boundary of the box do not affect the ultimate law of that you get, the law of the uniform spanning tree on ZD. So I called it a uniform spanning forest rather than a uniform spanning tree. For d less than or equal to 4, you get a spanning tree. Well, for d bigger than or equal to 5, it's a countable collection of disjoint trees, and so it's called a forest. I'll explain in just a moment after I've shown you Wilson's algorithm in that context. So we can also use Wilson's algorithm for Z2. It's basically the same as it is for a finite graph. So you choose an ordering of Z2. You start off with Z0, and then you do exactly the same thing that you did before. And you get the same law for all choices of the vertices Zi. And you can, in fact, choose this in a kind of adapted way. In other words, providing you're not stupid, you can choose Zk to depend on the tree that you see so far. Now, in fact, in 2 dimensions, we can define loop arrays random walk. Well, we can actually start off in 2 different ways. Here, we start off with a single point, but we can also define the loop arrays random walk from a point x to infinity by taking the weak limit as z tends to infinity of the loop arrays random walk from point x to the set z. So an alternative first step in the 2-dimensional loop arrays random walk is to take a loop arrays random walk from some point to infinity. And let me comment that Wilson's algorithm also works for ZD with d bigger than or equal to 3 if we just start off with a loop arrays random walk for some point to infinity. And now I can answer Bertrand's question. Supposing that we're now in Z3 and the first couple of stages of, in Z5, and the first couple of stages of the loop arrays random walk are like that, and I now choose another point and I run a loop arrays random walk from here to this set. Actually, sorry, I must erase this because what we're going to get is the first stage was to take a loop arrays random walk from Z0 to infinity. So it's like that. Now I choose another point. In d bigger than or equal to 5, 2 simple random walks may not intersect. So that one might not intersect the first structure. And so we'd have 2 things disconnected. And then subsequent stages We might make connections to one of or the other of them, but we can never join the two up. And it turns out that hitting a loop array's random walk path and hitting a simple random walk path have the same ultimate probability. In other words, you either do it or you don't, even though loop array's random walk paths are thinner than simple random walk paths. So that's what's going on in Z2. And here's a not very illuminating picture of the part of the loop uniform spanning tree in Z2. It's the sort of thing you can give to your children to trace paths across if you want them to keep them busy for a quarter of an hour. And so here's just a sort of illustration of loop array's random walk. I believe my code, so there isn't actually a loop there, but it certainly looks like it, doesn't it? So you take a point here, and you run a path to there. You take another point, you run a path, you take another point, and so on. And after a while, you'll get your loop arrays. You'll get your uniform spanning tree. So in order to study the uniform spanning tree, we need to know things about the loop array's random walk. And so I'm going to give you a very brief, concise history of the loop array's random walk. So it was introduced by Greg Lawler in 1980. And he proved that for d bigger than or equal to 4, the scaling limit of the loop array's random walk in ZD is Brownian motion. In 2000, Schramm studied the scaling limit of the uniform spanning tree in 2 dimensions. That was the paper that introduced SLE. So even if uniform spanning trees were completely unimportant for any other reason, they would already have a major place in history because of this. And he conjectured that the scaling limit of the loop array's random walk in 2 dimensions is SLE2. And the fact that these 2's are the same is kind of a coincidence. At least I think it is. So Lawler, Schramm, and Werner in 2004 proved this result, and that the scaling limit of LEW2 is in fact SLE2. And Garde-Cosma, in a paper I've already mentioned briefly, found that the scaling limit of the loop array's random walk in 3 dimensions exists. 3 dimensions is the only really hard dimension for the hardest dimension for the loop array's random walk. And although this is a sort of 100-page paper, he gets the scaling limits, but we really don't know very much at this point about 3-dimensional loop array's random walks or their scaling limits. Now, one of the key things that we're going to want to know about is the length of loop array's random walk. So I'm going to define the growth function. We look at a loop array's random walk from the origin to the boundary of the Euclidean ball of radius n, and I'm going to call that random variable mn. We take its expectation, and that's LDN. Then Greg Lawler's results give that LDN goes like logarithmically asymptotic to n squared for d bigger than or equal to 4. In fact, it's properly asymptotic when d is bigger than 5, and it's got a log correction when d is equal to 4. Now, I'm going to talk almost entirely now about what happens in 2 dimensions. And Rick Kenyon in 2000 showed that L2n is logarithmically asymptotic to n to the 5/4. He was actually using dimer coverings, not SLE, to obtain this result. Out of chronology, but helpful to put here, is that Greg Lawler then improved that in 2014 to show that it's actually bounded above and below by constants times n to the 5/4. So we're going to write kappa to be the growth exponent of the LEW in 2 dimensions. Working with a student of Greg Lawler's, Robert Masson, in 2010, we proved furthermore that we have kind of tightness of mn over n to the kappa. So the probability that it lies between constants times n to the kappa is bigger. Well, the probability it's not like in that interval is dominated by a stretched exponential involving lambda. And we actually got bounds not just for the loop array's random walk in a ball, but bound in a domain D, or some general domains D in Z2. So we wanted to study the geometry of the uniform spanning tree. And although the uniform spanning tree has got a much more complicated dependent structure than percolation, it turns out to be easier to study. And I think the reason is because when we're looking at percolation, we're not interested just simply in the sort of probability of two adjacent bonds being open or closed. What we're interested in is the structures which the open bonds create, in other words, paths in percolation clusters. And we don't know that much about paths in percolation clusters. In uniform spanning tree, the paths are loop arrays random walk paths, so we know the law of the paths in the uniform spanning tree. So something which would be incredibly useful to have for other models is given to us more or less at the beginning for the uniform spanning tree. So, of course, also, everything is a tree, and that makes sort of things easier too. So we can look at geometry of the uniform spanning tree, either its intrinsic geometry or the Euclidean geometry. So we define the intrinsic metric, which is just the shortest path in the tree between 2 points, and I'm writing that for du. And then we have the intrinsic balls, and then, of course, we have Euclidean balls. And since the paths of the loop arrays random walk are quite rough, one expects that the intrinsic balls should be much smaller than the Euclidean balls. And in fact, by Wilson's algorithm, the distance from the origin to a ball of radius r should be about the length of the loop array's random walk from 0 to the boundary of the ball, in other words, roughly r to the kappa. So it's natural to guess that, in some approximate sense, the relation between the Euclidean and intrinsic balls should go like that. So here's just a picture showing the previous picture. We have here the origin, and the distance, if this is the ball of radius r, the distance out to the ball of radius r is going to be along this loop array's random walk path here, which has length probably about r to the kappa. So that's why we should see the two geometries related in this way. But we can make things a bit more precise. And so here's a result from my paper with Robert Masson in 2011. So for lambda bigger than 1, the probability, so we can look at the intrinsic Euclidean ball of radius r and intrinsic balls of radius r to the kappa, which we then weight by a factor lambda. And the probability the intrinsic ball is not contained in the Euclidean ball is dominated by a stretched exponential like that. On the other hand, we look at the probability the intrinsic ball blown up by lambda does not contain the Euclidean ball, and we have a polynomial type bound on that one. And very quick idea of the proof is we're going to use loop arrays random walks to construct the uniform spanning tree in 2 dimensions, and the estimates that we have on the length of paths to study balls in the metric. Now, you notice that there's a difference between the nice exponential bound here and the polynomial bound that we have here. And so why is that? So what the bad event that we have is that we have an intrinsic ball, which might look like that, and so that a smaller Euclidean ball is failed to be contained in the intrinsic ball. And to see why we should only expect a polynomial bound here, let's look at the following picture, and remember how you construct the uniform spanning tree in 2 dimensions. So you start off with, one way of starting it, as we saw, is to take an infinite loop arrays random walk starting from 0. So here is this infinite loop arrays random walk starting from 0. And with a bit of work, one can show that it's got a probability at least k to the minus delta, for some delta, of returning inside the ball of radius r after leaving a ball of radius kr. And if this event occurs, and here is something where it does occur, then these points here are in the Euclidean ball of radius r, but they're a long way away from the origin in the intrinsic metric. So I have, as you see, a program which will construct loop arrays random walk paths, and I had to run it about 15 times before I got the behavior I wanted from the in the slide. So the probability of a bad event is big in polynomial terms, but you don't see it very often if you do simulations. So this is why we have the difference between the two types of inclusion for the of balls. And here is a picture produced by Robert Masson showing the uniform spanning tree again, and in red, actually, you can see an intrinsic ball of some size. So actually, the center is about here, and you can see that there are some bits of the complement of the ball digging in quite close towards the center. We wanted to look at random walks on these objects, and so we also wanted to know about volumes of balls. So since the Euclidean ball is about, the intrinsic ball is about the Euclidean ball of radius r to the 1 over kappa, we would expect the volume of the intrinsic ball to be about r to the 2 over kappa. And so we were able to prove stretched exponential type bounds on the error probabilities that we have here. So the upper bound follows immediately from theorem A, but to get for the second bound, if we just use theorem A, we'd only get a polynomial type bound, so we actually had to work a bit more. The point is that even if the intrinsic ball, as here, does not contain a nice Euclidean ball, it nevertheless contains Euclidean balls in some places, and we were able to use that fact to get the exponential type bound in form. So let me just say, when we proved this result, we felt that we knew quite a lot about the comparison between the intrinsic and Euclidean geometry. And it wasn't until we started on the second set of work, or I started on second set of work with Takashi Kumigai and David Croydon, that we realized that actually there were some important things that we had not proved. So let me now tell you what we did not prove. So let's write Gx for the event that the intrinsic ball is contained of this radius is contained in Euclidean ball of radius r. The law of the uniform spanning tree is stationary, and so theorem A gives an exponential type error probability on this probability of the complement of this set. Now let's look at the event that we look at a Euclidean ball of radius r, and for all points x in this Euclidean ball, we require the intrinsic ball, center x, of this radius to be contained in the Euclidean ball, center x and radius r, which would be contained in the ball, center 0 and radius 2r if we wanted. So it's the intersection of all these events g of x. Then theorem A, we have a simple union bound, so the probability of this event complement is bounded by r squared times e to the minus lambda to the 2/3. So if we fix lambda, shall we say, equals 200, so relying quite the probability of this event is then extremely small, and we now want to look at limits as r tends to infinity. As r tends to infinity, this bound becomes completely useless for a fixed lambda, and so theorem A does not exclude the possibility of having some large, thin, exceptional balls in this set. They have to be thin, because if we choose a point at random, it's not going to be in the ball. But we might have a sort of decent structure here, and then there might be some very thin, exceptional balls which look like that, which we don't find very easily. I mean, of course, we don't believe that's going to happen. In fact, it doesn't. But my work with Robert Masson did not exclude that possibility. OK, so let's just show you this very nice picture showing you the comparison of the Euclidean and intrinsic metrics. So here we have the end of the picture, which shows you a tree. And what we have here is, first of all, the uniform spanning tree with its sort of Euclidean geometry. And then by some clever algorithm, he unwinds the tree and gets the tree now in its intrinsic geometry. And I'll do it one more time before we go on with the math. But it's somebody called Mike Bostock's Visualizing Algorithms, and you can find it on the web quite easily to watch as often as you want. Now I need to remember the magic command on the Mac to restore. So now I want to go on and talk about scaling limits of the uniform spanning tree. And I'm going to give you a fair amount of history from Schramm's paper of 2000. So perhaps being a complex analyst, starting off, Schramm took a map from R2, or the complex plane, into the S2, which is conformal, and we'll map infinity, shall we say, to the North Pole. And we are going to rescale the uniform spanning tree by a factor delta. So we map delta Z2 into phi of delta Z2, and we're going to call that S2 delta. And we now look at the uniform spanning tree on this set, which is also embedded into the sphere. And when you're looking at scaling limits of discrete objects like that, the first thought that you might have would be, let's write u tilde delta for the real tree obtained from this by adding an interval at each edge. So you have your sort of formal tree, and you just add little line segments to get a continuous a metric space which is connected. And we define the Hausdorff metric on subsets of S2 in the following way. If you have a subset, we define the expansion of that set by epsilon. So we can look at the Hausdorff distance between two sets by looking at the smallest epsilon, so that each of them is contained in the epsilon expansion of the other one. So we can look at limits of u tilde in this metric. But a few minutes thought tells you that this is a bad idea, since the Hausdorff distance between u tilde delta and S2 is going to converge to 0, since you're just looking at sets. You're looking at a pretty dense subset, and as they converge, you just get the sphere. So this kind of convergence is completely not useful in this context, because we're losing all the structure about paths in the set. So this is what Schramm did. For x and y in S2 delta, we take the path in u tilde connecting x and y. And we're going to look at the compact subsets of S2 with the Hausdorff metric. And we're going to look at the following object, which we call the paths ensemble of u tilde delta. So we have a point in S2, a point y in S2, and the path in the compact subsets, which connects x and y, omega x, y. So we have these objects, and then we take the collection of all those objects. So what we get is a random closed subset of this space S2 cross S2 cross HS2. And we write Q delta for the law of the thing that we get, I delta. Now, M is compact because we've set everything up so that it is. So the space of H of M is compact, and so is also the set of probability measures on H of M. So with no cost at all, the Q deltas are tight, and so there exists subsequential scaling limits. So without doing any hard work at all, we can see that there would be some kind of scaling limit in this framework. And the scaling limit is going to have information about the limits of I, and so about the limits of paths in this setup. Well,
other dimensions?
I mean, this would works in pretty much any space that any compact space or space that you can compactify. You can do this. So, I mean, in some sense, at this point, Schramm had not done that much. But of course, what was really great about his paper was the subsequent investigations he made on the limit that you get. So let Q be a subsequential limit of these Q deltas. Then Q almost surely, if you take 2 points in S2, omega xy is just some compact set, but almost surely we get a simple path out. He defined the trunk, which is the collection of these paths minus the endpoints. And if you work in real trees, or familiar with things like Alders's continuum random tree, these objects are kind of hard to visualize because almost all the mass of the object is actually on the endpoints. The trunk, which is just a countable union of line segments and is somehow much smaller than the rest of the tree. So this is what Schramm called the trunk. This is Q almost surely a real tree which has degree 3. And he showed that the Hausdorff dimension of the trunk is the same as the limit of the Hausdorff dimension, or the Hausdorff dimension of the limit of a loop array's random walk path. And at that point, he didn't know what that was, but was proved later by Lawler, Schramm, and Werner to be 5/4. Well, no, they.
Is that just a consequence of Cantor's stability?
Sorry?
I mean,
Yes, I think it's. I think it just comes because it's a countable union of those things. I mean, his actual statement was, if the Hausdorff dimension of the limit of the loop array's random walk lies in an interval, then the Hausdorff dimension of the trunk lies in the same interval. And then, of course, it could be improved when people did get better results. So he then went on to look at scaling limits of these paths, conjectured these were given by SLA2, and as I said, this was proved by Lawler, Schramm, and Werner in 2004. So Schramm's limit gives the results on the topology of the limits of the uniform spanning tree, but information about measures and metrics on it are lost by this approach. So what one would like is a limit in a better space which captures more information about the uniform spanning tree. And so there's been lots of development in the real trees since 2000, work of many people, Duquesne, Evans, Grevin, Lagarde, and as I said, many others. And so we're going to build a better space for looking at limits of uniform spanning trees. So as I said, a real tree, I'm not going to define it. It's basically a metric space with a tree-like structure. And we're going to look at a space of real trees with measures, roots, and embeddings. So we have T dt, a locally compact real tree, a measure on the tree, a map from the tree, which is a sort of abstract object, into R2, and a root in the tree. So that's going to be the space that we're going to be working on. And then, of course, we have to define metrics and topologies on this space. So I told you already about the Hausdorff metric. If we have two metric spaces, we look at isometric embeddings of those metric spaces into a third metric space, z dz, and we define the Gromov-Hausdorff distance between x1 and x2 to be the infimum over embeddings of the Hausdorff distance between x1, phi of x1, and phi of x2. In other words, the images of x1 and x2. So that's a way of comparing the distances between two metric spaces, in particular two real trees. Then we also want to compare the measures, and so there's the Prokhorov metric on measures. So we have two measures on a space, xd, and the Prokhorov distance between them, this arises in theory of weak convergence, is we look at the smallest epsilon, so that for all closed sets, mu1 of A is less than epsilon plus mu2 of the expansion by epsilon of A, and similar thing the other way around. And if the measures have support K, then because we have to sort of cover each set with the other set, the Prokhorov distance between two measures is going to be bigger than the Hausdorff distance between the two sets. So we now look at the Gromov-Hausdorff-Prokhorov metric. Given metric measure spaces, xi, di, mu I, you look at the infimum of Prokhorov distance between isometric embeddings of these things into another space. So we defined our collection of trees to be this quintuple here, and with the machinery that I have now introduced, we do more or less the obvious thing. We use the Gromov-Hausdorff-Prokhorov distance between the metric measure spaces that we have here, which are trees, and then some extensions to handle the embeddings and the roots. And so with this framework, we now have the following result. So given a uniform spanning tree and writing phi for the natural embedding of Z2 into R2, we define the rescaled tree U delta to be this is still an abstract object, the tree, the metric rescaled by delta to the kappa, the measure scaled by delta squared, the embedding rescaled by delta, and the origin not rescaled by anything. And we write P delta for the law of this rescaled tree U delta. Then our first result is the laws of U delta are tight. So once again, we do not get convergence of these things, but we get subsequential scaling limits. So we now take one of these subsequential limits. The limiting object has Hausdorff dimension 8/5, 2 over kappa, which is, remember, the volumes of balls in the original for the uniform spanning tree. The measure mu t gives measure 0 to the trunk, and we have the following sort of estimate, well, the following estimate for mu t of balls in this space. So we have the r to the kappa term with then some kind of logarithmic fluctuations, and we get other properties similar to those that one has in Schramm's theorem. So I'm just going to copy the result onto this slide again. And let's just say where we get, so quite a number of the properties are ones that we had, that Schramm already had. But the way that we have gone on beyond what Schramm could do was that his theorem was able to give topological information about the limit. But here we've also got results using an intrinsic metric on the limiting tree and results involving a measure on the tree. And those metrics and measures were missing from Schramm's framework. We also got some results on limits of random walks on the uniform spanning tree in terms of a limiting diffusion on the real tree. Gwendolyn?
Yeah, just have a little question to understand your notion of convergence. Is that more or less equivalent to saying that if you take, I mean, on the spherical metric, any Poisson point process of point chosen with respect to the to the natural measure on there, finite set of points that you choose uniformly at random, and then looking at the law of the finite tree there and saying that the paths and the tree, including parameterization, is sort of converges in some nice topology. Is that something more or less the same, or?
Doing something similar to that is an essential part of the proof. I mean, the ultimate statement, you know, involves not just looking at sort of subtrees spanned by k points, but looking at the whole space of trees. But the way you get the convergence of the space of whole trees is by looking at various kinds of subtrees spanned by these things. So let me just say a little bit about the proofs. So back to the uniform spanning tree, let's write nr epsilon to be the smallest cover of an intrinsic ball of radius r by balls of radius epsilon. And MRS is the biggest Euclidean distance between points in an intrinsic ball of radius r. So we look at an intrinsic ball of radius r, we look at points which are distance no more than s apart in the intrinsic metric, and we look at the biggest Euclidean distance between those points, and we write that for MRS. Then it turns out that proving tightness of the U deltas, reducing to proving that the following three quantities are bounded in probability. So first of all, we look at the measures of balls and we rescale them in the right way. We look at the number of balls needed to cover an intrinsic ball, and then we look at the maximum distortion that we get between the intrinsic metric and the Euclidean metric, or one-way distortion. So 5 was proved already in the earlier papers by Robert Masson and myself, but 6 and 7 required new properties of the uniform spanning tree, and in particular to show that to handle this quantity nr epsilon, we need to know that there are not these large, thin, exceptional structures, which I already pointed out are permitted by the earlier results. So we needed some new properties of the uniform spanning tree, and that's basically, well, one of the results at least that we needed was there are no large, thin balls. So these could occur in a number of ways. One way could happen if a loop array's random walk path were to double back on itself like that, then if we look at the uniform spanning tree ball center, this point here, it just consists of this sort of line segment or the path that we get there. So we'd have a large, thin ball. Another problem we have is that the loop array's random walk is not Markovian. So what we were able to, in the earlier paper, we showed that if you look at the length of loop array's random walk from the origin to the boundary of a set, it's going to be of length about n to the kappa. But what you could have conceivably occur is that you have a nice sort of fractal path here, then you have a long, thin segment, long, straight segment like that, and then you have another nice little fractal bit like that. So there could be long, thin, long straight segments or nearly straight segments in loop array's random walk paths. Of course, no one believes for a moment that there are such things, and in fact there aren't, but you have to prove it, and simple estimates on the distance here are not enough to prove it. And one would also like to have, with high probability, the following. So we take two boxes in Euclidean space. Typical loop array's random walk path between, if we look at loop array's random walk path starting here and ending there, then the estimates that we had will tell us that that path is reasonably long. But there are a lot of other paths between these sets, and we want to exclude the possibility that somewhere else there might be a path which is much too short. And so let me try and give you the basic idea that we had to prove these results. We're going to take a scale n, a number n, and a sort of acceptable distortion parameter lambda, and we look at a discrete set which is n over lambda times zd. The uniform spanning tree is a one-sided tree. This is something I forgot to mention or didn't mention earlier. And so for each x in D, gamma x, I'm going to write for the unique infinite self-avoiding path in U starting at the point x. And by Wilson's algorithm, this has the law of a loop array's random walk from x to infinity. So let Zx be the point where gamma x leaves the Euclidean ball of radius n. And we define a good event fx to hold if there's a point yx in our special set D close to the exit point, such that the path gamma yx hits gamma x close to yx, plus a number of other nice properties. So the picture, actually let's draw it on the board, and then I'll show it to you next time. I'm going to take my balls to be boxes. So here is the boundary of the ball radius n. Here is the, here is the loop array's random walk, which we start off our construction. And then we have these grid points in D, like that. And what we want is that there's one of the grid points y, so that when we now, this is our first step in the construction of the UST. We now construct the we're now going to take this point and run a loop array's random walk from here to here. The bad thing that would happen is if that loop array's random walk wanders away like that. The good thing is if it comes in and hits close by. So here is the picture and that we have. Here is our loop array's random walk path going out. And the good event, this is supposed to be the good event, that we have a loop array's random walk from here coming in and hitting here. And the bad event, there isn't enough room to show a really bad event, which should be the thing going out a long way and then coming back in and hitting things. So we want there to be a point in our discrete set D where this path hits here, hits the original path fairly close to its exit point. There we are. So if we define this event, good event fx, the probability of the complement of that is bounded by a stretched exponential. So we now look at the intersection of the fx's, not over all x's in a ball. Actually, there's a misprint there, that should be 0. Not over all x's in a ball, but just over x's in this discrete set with separation n over lambda. So the number of those points in this intersection is about lambda to the p, and so we get a bound on the probability of f complement of this kind, so lambda to some polynomial, e to the minus lambda to the c, so bounded by e to the minus lambda to the epsilon. There's lots of room to put other nice things into the event fx, and one of them is that the distance between u and the point zx. So this is going to be the point here, zx. We want that the distance between x and zx is also of the right order. So let me just go on here. Oops, sorry, wrong way. So the path from x to zx is good. The point from yx to zyx is also good. So what we get is a family of good paths in our uniform spanning tree, which are the right length at scale n. And we can fill in the rest of the uniform spanning tree and obtain good behavior uniform over a large region. And then by varying the scale n, we actually get families of paths which are good over a wide range of length scales. So these results enable us to uniformly control the size of balls and the relation between metrics and measures, and hence obtain tightness of these U deltas. And final question is, we only got subsequential limits, and of course one would like limits. And so the key difficulty about getting limits is the metric on the uniform spanning tree. So the metric is the length of a loop array's random walk, and so we need to know about the rescaling of the length of loop array's random walk paths. So Lawler, Schramm, and Werner proved LEW converges to SLE2, but their metric did not give information about the length of paths, or it was invariant under a class of time changes. Let's set Mn to be the length of loop array's random walk from 0 to the boundary of the Euclidean ball of radius n. Then we'd have tightness for the rescaled value random variables Mn. In other words, we have this, and that gives us subsequential limits of these lengths, of these rescaled lengths Zn. So we can conjecture that actually, as n goes to infinity, the random variables Zn converge in distribution to this random variable Z. And this is very closely related to a problem which Greg Lawler has been working on for some time, which is the convergence of loop array's random walk in its natural parameterization. I think he's optimistic about being able to prove this, but as far as I know, he hasn't done so yet. And so when he does, I think, or if he does, but probably when he does, one will then be able to sort of improve with results like this. We ought to be able to move from subsequential limits to limits. Has he proved it?
Sorry to jump in, but I happened to be in Chicago last week, and so it will be when he does.
When he does.
He
Okay.
confirmed that.
Okay. Right. Yes. Fine. Good. Good. Okay. So yeah. So that's the end of my talk, and I just thought I'd show you a picture by Russ Lyons showing some of the fun things that you see in the uniform spanning tree. So let me tell you what the picture is. We've got a uniform spanning tree here on this 200 by 200 grid. Of course, there is a path in the uniform spanning tree from the origin to the point 200, 200. And what we then get is the path in the uniform spanning tree connecting these 2 points. And then the vertical scale gives the distance from points in the uniform spanning tree to the origin. And of course, the noticeable feature that you see here are these big cliffs. And those big cliffs arise because we are in a tree. So there are going to be regions where, in order to get from here to points here, you have to go round a long way, and then the sort of claws of the tree come back. So we get these nice-looking cliffs running through here. And in fact, because the dual of the uniform spanning tree is also a uniform spanning tree, the boundaries of these cliffs are also actually SLE type curves. Okay, I'm finished.
Yes, do you have results on the degree of the branch points? So I presume that they are all of degree 3.
Schramm, yes, I mean, we can take Schramm's results, transfer them into our setting. So he proved that almost surely the maximum degree is 3, and so that's also true in our context.
I mean, you didn't mention the contour. I mean, the way to describe the uniform spanning tree by the, Peano curve that winds around.
No,
I was wondering whether, I mean, if you want to just, exclude the possibility of having these long, thin channels, whether this is not part of the convergence to SLE8, because if you would have a long channel, that means that the Peano thing would do something and create a pocket, and which is so. Is that sort of, do the arguments you use are sort of similar to the ones we used to?
We have we have not used this Peano type construction. I mean, one problem is if you want to get results on the discrete uniform spanning tree, getting things back from the limit, you tend to, it can be a little tricky to get stuff back from the limit because you don't quite know how all of these quantities behave in.
Right, but what I mean is that sort of when you want something uniformly on all points, if you have convergence of the contour thing encapsulates sort of everything. So the discrete one. So if you have convergence of the discrete contour to the continuous one, we have sort of it.
Yes. This is not how.
Be useful. I mean,
it might be useful. But this is not how. This is not how. In fact, we did it.
Is it possible to do the same construction you did for the loop raised walk, except using SLE on the reals? For example, taking some sort of dense countable subset and doing the same procedure.
Yes, I mean, I would imagine so. In fact, maybe you should ask Wendelin. I mean, an obvious question is, can you then construct, you construct a limit by choosing points, running SLE type curves, in other words, mimicking Wilson's algorithm in a purely continuous context. That's not something one would imagine that it should work. We, at any rate, have not proved that it works, and as far as I know, no one else has done that either. But I'm not. Yeah.
it's not.
There may be. Okay.
I don't think there's any problem in.
No, I mean it's something which should work, but no one has, as far as I know, actually written a paper saying yes, it does work.
People are working on that.
Right. Okay. Yeah.
Anyone else? Not. Let's thank Martin again.